Let me take you through this example where we'll find the area of the region bounded by this function, x cubed plus 1, and the x-axis between the vertical lines of x equals 0 and x equals 1. We're going to find that area by finding the limit of a Riemann sum using this formula that I'm going to jot down here. And don't worry, I'll explain to you what the formula means in just a second. The area is going to equal the limit as n approaches infinity of the sum from index 1 to n of f at x sub I times delta x. This formula just tells us that what we're going to do is we are going to break up this area into an infinite number of rectangles and then add the areas of all of those rectangles together to get the area under the curve. Now, the best way to visualize that is for me to draw a finite number of rectangles inside the area under this curve so that we can understand how this formula works. So let me start by doing that. Maybe I'll break this area up into just 4 intervals just for simplicity's sake. So I've got interval 1, 2, 3, and 4. And within each interval, I'm going to create a rectangle that is going to help me approximate the area under this curve. And I'm going to use the right endpoint of each of these intervals to give me the height of the rectangle I'm going to draw. There we go, I've drawn the 4 rectangles. Notice that if I were to add the areas of all 4 of those rectangles together, I would get an over approximation of what the actual area under the curve is, because I've got all these extra little areas that you see in green there that aren't actually under the curve. But you could imagine that if I used more and more and more rectangles, making the width of each interval infinitely small, I would get a perfect approximation of the area under the curve. And that's what this formula says. In this formula, we have a lot going on. Firstly, let's analyze this part. This just finds the area of a rectangle. This just does the base width of the rectangle multiplied by the rectangle's height. And then it tells us we're going to do a lot of these area calculations. We're going to do a lot of base times height calculations. In fact, we're going to iterate through this sum from index 1 all the way up to n, and we're going to let n approach infinity. So basically, we are going to find an infinite number of products and add them all together. But let's see if we can come up with expressions for the height and base width, and then use math to be able to simplify this so we don't actually have to do an infinite number of calculations. Let's start by looking at how can we come up with an expression for the width of each base of n rectangles. Well, what we do, we look at what's the width of the original interval. Well, the question said we were starting from an x value of 0 and we're going up to an x value of 1. So the width of the original interval is 1. And I can calculate that by doing the end point b minus the starting point a. So 1 minus 0. And then divide that by n. How many intervals do you want to break this up into? If I wanted to break it up into 4 intervals, I did 1 divided by 4 to get 0.25. If I want to break it up into n intervals, I just do 1 divided by n. So let's jot that down. The base width, which we call delta x, is equal to b minus a over n. So for this question, there's my a, there's my b. So I do 1 minus 0 over n, which is just 1 over n. So in my sum, I could replace delta x with 1 over n. But what can I replace x sub I with? Let's look over here at the diagram as well. The first thing I want you to notice is I used the right side of each interval to determine the height of the rectangle. So for interval number 1, I used 0.25. So I will call that my x sub 1. That was my first x value I used. For interval number 2, I used this point right here for the height. So I'll label 0.5 as my x sub 2. And then for my third interval, I used this point as the height. So I'll call that my x3. And for my last interval, I used that as my height. So I call that x sub 4. When we use the right endpoint of each interval to determine the height of the rectangle, it makes working with the formula a lot easier. Because notice, to calculate what x1 is equal to, we just go to our a value and add delta x one time, right? Delta x in this question was 0.25, so I had 0.25 once. If I wanted to calculate my second x value, I would add delta x to a once, twice. Add delta x and another delta x, and that gets me to x sub 2. And hopefully you can see how this works, right? If I want x sub 4, how many times do I add delta x to a? I add it I times. I add it 4 times. So we can jot down how we would calculate my x sub I value right up here. X sub I, we will calculate by going to our initial value and then adding delta x I times. As we do the sum, the I value goes from 1 to 2 to 3 to 4 all the way up to n, so the I value matches the interval number we are working with. Now in this x sub I formula I've created, let's sub in what we know from this equation. The a value is actually 0, and my delta x value, we just calculated above, is 1 over n. So I can replace that with 1 over n, and then if I simplify this, it's just I over n. So now let's work with our limit formula and sub in what we've just calculated. The area equals the limit as n goes to infinity of the sum from I equals 1 to n of f at x sub I, but x sub I is just I over n we calculated, times delta x, which is 1 over n. And now I can replace f at I over n because I know what my f at x function actually is. Remember? Let me jot it down up here. F at x is actually, look back to the question, f at x is x cubed plus 1. It's right here. So if I want f at I over n, I just take that I over n and replace the x in x cubed plus 1 with that. So let me rewrite the limit statement and replace f at I over n with I over n cubed plus 1. And that has to be multiplied by delta x, which is 1 over n. And now it's just a matter of simplifying this formula and evaluating the limit. So as I work with this formula, perhaps what I want to do first is distribute this 1 over n into both terms. So 1 over n times I cubed over n cubed is I cubed over n to the 4. And then when I distribute to the 1, it's just 1 over n. And now using my summation rules, I know I could rewrite the sum of term 1 plus term 2 as the sum of term 1 plus the sum of term 2. So let me write that. And what I can do next, I can move any constant factors in front of my sigma. So we treat n as a constant because that's the number of intervals we're breaking it into. So as I find the products and add them together, well, with each product, right, each area I calculate, n is going to be the same value. So I can treat n as a constant and move any factors of n in front of the sigma. So for the first sum, I'm going to move 1 over n to the 4 in front. And for the second sum, I'm going to move that whole factor of 1 over n in front, leaving me with just a 1. And now I'm going to rely on your understanding of some basic summation rules. You have to know what the sum from I equals 1 to n of I cubed is. That's just a general formula you have to remember. And also you'll have to know what the sum from I equals 1 to n of a constant is. So I'll write those rules here as we do them. The sum from 1 to n of I cubed is n squared times n plus 1 squared all over 4. And the sum from 1 to n of the constant 1, you just multiply the constant by n. So that's just 1 times n, which is n. And now let me simplify inside the brackets before I even attempt to try and evaluate the limit. I notice that I can cross off both of those n's with 2 of those, and I can cross those n's off. And then n plus 1 squared is n squared plus 2n plus 1. So that is all over 4n squared. And then I've got this plus 1 here. I might want to get a common denominator. So I'm going to change that 1 to 4n squared over 4n squared. And then I'll collect my like terms, my n squared plus my 4n squared. And now that it's fully simplified, now I'll attempt to evaluate my limit. And when evaluating a limit at infinity, of a rational function, divide all the terms by the highest power of the variable that's in the denominator. So I'm going to divide everything by n squared. So I can just write that I'm going to multiply the top by 1 over n squared and the bottom by 1 over n squared. And then I'll show you what I get when I do that to all the terms in the numerator and denominator. I would get 5 plus 2 over n plus 1 over n squared all over 4. And then as n goes to infinity, I know that 2 over n and 1 over n squared are both going to go to 0. So all I'm going to be left with is that my area is equal to 5 plus 0 over 4, which is 5 over 4, or 1.25 units squared. So that's the exact area under the curve. And we found it by finding the limit as the number of intervals went to infinity using a Riemann sum. Let's do another example, and we can do this one more quickly. Find the area of the region bounded by the graph of 4 minus x squared and the x-axis between x equals 1 and x equals 2. We'll do this again using the limit of a right Riemann sum. Let me rewrite the formula for you. The area equals the limit as n goes to infinity of the sum from 1 to n of f at x sub I times delta x. And now let's start by calculating the base of each of the rectangles. Maybe I should draw some rectangles in here just to help you visualize it as well. Let me do that really quickly. I'll break it into 4 sections again. So let me draw 4 rectangles. I was actually only able to draw 3 because in my 4th interval, let me just label my intervals for you. I've got my 1st, 2nd, 3rd, 4th. The right endpoint of my 4th interval, which is right here, I'll call this x sub 4, is 2. So if I use that as the height, the y value there is 0. So the height of that rectangle is 0. So notice this is going to be an under approximation. We're missing all of these areas if I just use 4, but you can imagine if I made the number of intervals approach infinity, they would start to fill all of this area and find us the area under the curve. So if I wanted to find the width of each interval that I have, what we do is we take our starting value, which we call a, and our end value, which we call b. We find the distance between them, so b minus a, and then divide it into n intervals by dividing it by n. So I can say my delta x, which is the width of the base, I get by doing b minus a over n. So in this question, here's a, here's b, so I do 2 minus 1 over n, which is 1 over n. And then when I get the height of each rectangle, remember this is the height, I use the right endpoint of each interval. So here is the first x value I would use, here's the second, here's the third, and I've got x4 already labeled. Notice to get each of them, I add delta x, which is the width of each base. I add that I times. To get the first one, I add delta x once, the second one, delta x twice, and so on. So remember the general formula for getting the height. We will use x sub I, which we can calculate by doing a, our initial value, plus delta x, I times. In this question, a is 1, plus I times my delta x is 1 over n. This could simplify to just 1 plus I over n. So now I can just work with my summation formula. Let me rewrite the limit. And now I can replace f at 1 plus I over n with the value of the function at 1 plus I over n. And remember, what is the function we're working with? It's 4 minus x squared. So I'm just going to write that over here. Remember, f at x is 4 minus x squared. So let me now replace x with 1 plus I over n. And now actually let me simplify this perfect square binomial I have right there. 1 plus I over n all squared. That's 1 plus I over n times another 1 plus I over n, which would give me 1 squared, which is 1, plus 2 I over n's, plus I over n all squared, which is I squared over n squared. And now let me just distribute this minus sign to all three of those terms and simplify everything underneath the square brackets. 3 minus 2i over n minus I squared over n squared. And this is all being multiplied by 1 over n. So let me distribute that 1 over n to all three of these terms now. So I get 3 over n minus 2i over n squared minus I squared over n cubed. And now I can distribute my sigma to all three of those terms. And now my summation rules tell me that I can move any constant factors in front of the sigma, so all of the factors involving an n can go in front. So for the first one, I can move the whole 3 over n in front, but I think I'm just going to move the 1 over n in front and leave the 3. The next one, I'll move 2 over n squared in front. And my last one, I'll move 1 over n cubed in front. And now hopefully you know your summation rules and you know the formulas for all three of those, the sum of a constant, the sum of I, and the sum of I squared. And I noticed I forgot to write my index of 1 to n on that sigma. So let me go ahead and use my summation rules to evaluate each of those sums. The sum of a constant from 1 to n is just equal to the constant times n, so just 3 times n, minus 2 over n squared. The sum from 1 to n of I is just n times n plus 1 over 2 minus 1 over n cubed. And the sum from 1 to n of I squared is n times n plus 1 times 2n plus 1 divided by 6. Now there's just a bunch of algebra to simplify all of this. So I'm going to see if there's stuff I can cancel first. I've got two factors of n being divided by each other there. I can cancel that one with one of those, and this one with one of those. And let's see what we've got left. So my area is equal to the limit as n approaches infinity of, well, my first term is just 3. And then my next term, I actually noticed those factors of 2 can cancel as well. So I'm actually just left with minus n plus 1 over n. And then my last term, minus, I've got n plus 1 times 2n plus 1, that's 2n squared, plus 3n plus 1, all over 6n squared. And now if I get a common denominator and combine all of these together, my first term, I would have to multiply top and bottom by 6n squared, which would give me 18n squared over 6n squared, minus my second term, I would have to multiply top and bottom by 6n, which would be 6n squared plus 6n all over 6n squared, and then minus the last term. Notice they all now have a common denominator, so I could write them as a single fraction. I've got 18n squared minus 6n squared minus 6n minus 2n squared minus 3n minus 1 all over 6n squared. And now I'm going to have to give myself some more room to work here. So what I'm going to do is I'm just going to take this and we'll move it over to the side here so I can write a couple more lines. I'm going to collect my like terms. I've got an 18n squared minus a 6n squared minus a 2n squared. So that gives me 10n squared. I also have negative 6n minus 3n, that's negative 9n. And my only constant is that negative 1. And now I can evaluate my limit. A limit at infinity of a rational function, divide all the terms in the top and bottom by the highest power of the variable that's in the denominator. So let's divide all the terms by n squared. Or another way of saying that, let's multiply the numerator by 1 over n squared and the denominator by 1 over n squared. And that'll make it easy for us to evaluate the limit. When I multiply everything in the top by 1 over n squared, I get 10 minus 9 over n minus 1 over n squared. In the bottom, 6n squared divided by n squared is just 6. And now as n goes to infinity, both of those terms go to 0. So I could say my area is equal to just 10 over 6, or 5 over 3, or approximately 1.67 units squared. And that's it. Let me zoom out so you can take all of this in if you want to review the whole thing. That's how we use the limit of a Riemann sum to find the area under a curve. Jensen Math.